The California Aqueduct supplies water to Southern California in the order of 3.6 million acre-feet per year. During its 30-year life, the aqueduct has been subjected to changes in the way it is operated and had its capacity increased by raising its concrete lining. This has put a greater demand on the canal's foundation. As a result, the lining has experienced excessive differential settlement, resulting in cracked or displaced panels. Since Southern California is so dependent on the delivery of Northern California water, DWR engineers had to increase the levels of the reservoirs downstream, then wait until fall to make the repairs when the demand for the water was lower. They also had to create a 24-hour-a-day repair schedule to keep the disruption of water delivery to a minimum.
This was a very accelerated schedule. We went to 24-hour a day and 7 days a week right off the start. We had already pushed our schedule about half of what we've ever done repairs like this before. So we were going to do a repair in approximately half the time that we do a repair like this even under accelerated schedules that we've had in the past.
Repairing the damage is a challenge in itself. But repairing it with acceptable disturbance to the demanding water delivery schedule creates an entirely new set of challenges. The first step of the repair is the dewatering of the pool.
To bring the water surface down so we could get in and actually begin the repair process, we have a general criteria of bringing the water surface down 2 feet a day so that the saturated soil that's left behind will have a chance to drain and won't weigh so much that it could slide into the aqueduct, creating further damage that we'd have to repair.
The slippery algae, sediment, and other debris that remained on the sides of the aqueduct were then thoroughly washed off to prepare the concrete surface for the inspection and repair. The sediment and debris remaining on the bottom was then removed with front-end loaders. Small cofferdams were then built to isolate the remaining water from the repair areas. Using small pumps, push brooms, and compressed air, the last remains of water and sediment were removed. At this point, DWR engineers took the opportunity to assess the damage to the panels. On both pools 49 and 54, they had found excessive damage they hadn't anticipated.
Usually it's pretty obvious when you've got a problem area. 54 was quite obvious. We saw some distressed panels. They were literally cracked and sunk into the foundation. So it was pretty easy to locate those points, and that was obvious that they needed to be repaired. Other areas, it's more difficult.
The repair area really wasn't evident when the water surface was dropping until it came down to a point where you could see a large longitudinal crack in the aqueduct. That was 1,400 feet long.
The sections needed over 3 times more work than was originally planned, but the repairs needed to get done in the same amount of time.
You never reduce the amount of work on these jobs. You always increase it, and you never increase the amount of time you have available to do it. You're always sticking by the same schedule that you set up, and you promise the water contractors that you'd be done by that time and you'd deliver water in that time. So,
when the concrete panels sufficiently dried, the cracks and potholes were filled with mortar to provide a smooth surface for the waterproof membrane. More extensively damaged panels were demolished using a hydraulic hammer. Front-end loaders removed the debris. New concrete panels were then installed to match the existing grade. One specific section in Pool 54 contained severely damaged panels at the bottom.
there are areas of the canal that do need to have the canal lining removed and the supporting foundation also excavated and replaced. We typically like to replace it with a compacted embankment, but that's very difficult under saturated conditions that you'd find when you dewater a canal. so we'll backfill it in with a slurry. We'll pump it in, vibrate it. Usually we go with one sack of cement per cubic yard of sand, or maybe two. Contractors like a little more cement with their slurry because it pumps easier for them, so they don't get as many clogs with their pumping equipment. So they'll usually add the extra sack on their cost just to make it easier for them to do it. Once that cures, we'll go back and replace the original canal lining with new lining. That's 4-inch thick concrete, and then we'll do our repairs right over the top of that.
The lining of the aqueduct was saw cut on the upstream and the downstream ends of the repair sections. Anchor trenches were excavated on each end of the repair and on the primary and secondary sides of the aqueduct. These trenches provided an anchoring point for the waterproof membrane to be placed on top of the existing canal lining. The brand of waterproof membrane used was Terranap. It is an elastomeric bitumen geomembrane, reinforced with a non-woven polyester mat. There were two types of Terranap used. The type used on Pool 49 had a non-woven fabric attached to one side of the membrane. The non-woven mat provided the friction required to hold the shotcrete in place for curing. The type of waterproof membrane without the fabric was used on Pool 54 because the sloped sides were not as steep and didn't require as much friction to keep the shotcrete in place. It was also used on the curves on Pool 54 because it is more easily sealed when overlapping. Both types of waterproof membrane are produced in rolls 4 meters wide by 100 meters long. There is more than one way to place a waterproof membrane.
At mile 55, the contractor thought it would be best to install it with a crane. He thought that we could hold one end down and then move the spool or the roll of the material across the canal. It's typically done the other way, where you keep the spool on the edge of the canal and you pull the loose end across. But this canal that they did at 55 is very steep. It's 1.5 to 1 side slope, very deep. It's 35 feet deep, I believe. So it made it a little more difficult to pull the material up the other end. We talked about using that at the other repair down south, but we were very concerned about the wind that we find down there.
In the Palmdale area, with the high winds that occur at this time of year, which were 20 to 35 miles an hour while we were there, it makes using a crane problematic. There's restrictions on how much weight a crane can lift in the wind.
The contractor was able to set up the rolls of waterproof membrane on DWR-designed spools mounted on an excavator. The crew was then able to attach a cable to the free end of the membrane roll with a specially constructed pulling beam. The membrane could then be unrolled across the canal from the other side. Communication between the crew members was crucial for safety and efficiency. Precise placement of the two vehicles on both sides of the aqueduct enabled the crew to place the waterproof membrane at a very productive pace. The 4-meter wide strips were overlapped approximately 9 inches and anchored on both ends. They were then fused together with a propane torch to create a waterproof seam. Where a roll of waterproof membrane came up short and the next roll was required to be attached, a strip of 18-inch wide membrane was welded to the undersides of each end, creating a waterproof seam. Working day and night, sometimes under adverse conditions, DWR was able to stay on or ahead of schedule.
We had 4 crews, 2 in the day shift, 2 in the night shift. When shift change came, the replacement workers came in. We set the roll down, exchanged crews, and just went right on laying the geomembrane.
It took a lot of creativity and planning to keep 2 of them not only in a site where they could work, but keep the material coming to them so that they could remain productive.
Every seam was tested using compressed air. Wherever a seam flapped or bubbled up, it was marked, retorched, marked again indicating the defect had been repaired, then retested. Concrete was then placed into the anchor trenches on both the upstream and downstream of the repair, and on both sides of the canal where the waterproof membrane was anchored. Wooden forms were constructed using half-inch thick plywood. Strips of plywood laid flat were used for foothold rungs, and 2x4s were laid flat on one edge to create a 2-inch high lip. Forms were built with relief cuts so they could be placed at the hinge point of the invert. They were spaced 12 feet apart from their inside edges to form alternating panels. They were secured using 2-inch screws, spaced approximately 4 to 6 inches apart. Staples were also used to secure the forms. The ends were then secured by attaching them to 3-foot-long stakes. The stakes were then cut flush with the forms. Shotcrete was used to construct the new panels.
Shotcrete is concrete. It has all the same components as concrete. It has a smaller aggregate in it to allow it to pump easier. It's really just air-blasted concrete.
It also contains polypropylene fibers for reinforcement. Slump testing the shotcrete is very important. It needs to have a 1.5-inch maximum slump in order to hold its form when applied to the side slopes of the aqueduct. Beginning at the center of the canal invert, the shotcrete was applied using a shotcrete gun with a 2.5-inch nozzle. It was leveled using a 10 to 28-foot long rolling screed. The screed was kept rolling using a hydraulic motor. It was slowly raised and lowered using cables taken in and let out evenly by a winching system. Plywood shields were kept at both ends of the application area to minimize overspray. After a panel was completely leveled and finished with the rolling screed, contraction joints were tooled in for crack control. A curing solution was then sprayed onto the wet shotcrete. After a minimum of 12 hours curing time, the forms were removed. The remaining alternating panels were then placed using the previously placed panels as forms. This is what happens when shotcrete is mixed too wet and placed on the side slope. To fix the problem, the shotcrete was allowed to sit for a short time, then leveled again with the screed. Another scheduled part of the project was the repair of damaged culverts at Pool 47. In all, 4 culverts were repaired. Settlement beneath Pool 47 caused structural damage to the culverts. There were cracks as well as voids in the concrete behind them. To make the repairs, concrete was removed from the damaged area and a special mortar was used to fill the voids and repair the areas. The mortar used is called Imaco, manufactured by master builders. It contains silica foam and polypropylene fibers. The mortar is exceptionally adhesive and has unique void filling and hardening properties, making it an excellent choice for this type of repair. There were a number of problems and challenges encountered in the repair process that future contractors could face as well. The first of these was the weather. The site was experiencing 30 to 40 mile-per-hour winds the morning the waterproof membrane placement was to begin. In addition to dealing with high winds, DWR engineers had a crew that had no prior experience placing waterproof membrane. So in the process of teaching the technique, they were also learning new ways to place membrane in windy weather.
We literally had guys sitting on it to hold it down, just to keep it in place, you know, human sandbags, human ballast. And if you didn't keep that leading edge down and the wind got under it, You know, it would lift 1 or 2 people off of the lining, you know, that were sitting on the lining or sitting on the membrane trying to hold it.
Sandbags were both placed and tied to the membrane edge facing the wind until the edges could be torched and sealed. There was also the problem of groundwater or bank storage seeping back into the canal.
The location that occurred was unique in the fact that we were crossing a canal fault. The original canal excavation had uncovered this fault and exposed it. Typically in faults, you have a lot of groundwater that's finding its way to the surface. That just is a least resistant path. And it occurred for a pretty long length of canal, since the canal in this section ran parallel to that fault. So we had a 300-foot section that was just leaking all the time. We'd put our membranes down, and it'd essentially be a waterbed underneath the membrane. It was very difficult to work with. We ended up having to cut patches, little holes in the membrane to keep that water coming up until we could get the concrete on top of it and weigh it down.
Once the pool was refilled, the weight of the water contributed to the shotcrete's force. The repair process of pools 49 and 54 began on November 4th, 1999. Both pools were repaired and back in service by the 20th.
It was very satisfying, because initially I didn't think we could do it in that amount of time. I didn't think so. I said, you guys are crazy. We can't do this kind of repair in this amount of time. And I was surprised that we did. And so that's a good feeling when you're done with a job like that. I think that's a great challenge for any engineer. You want him to do something, tell him he can't do it. He'll get it done.